So first things first is I'm going to teach about homeostasis. I'm going to show a list of different vocabulary that I'm going to touch along the way. So I'm just going to write these out, and then I'll touch along these as I teach. So this will just take a second. Don't mind the baby in the background. He is just having a party back there. He's loving his mama. So first things first, I'm going to touch on the homeostatic control system here. So this will deal with a stimulus. This stimulus can be something such as cold weather, hot weather, loss of blood volume, increase of blood volume. It's something that will cause a change in a different variable. This stimulus will then be picked up by a receptor. This receptor will then transmit a signal through the afferent pathway, which will then bring that signal to the control center. That control center will then find out what's going on and then respond appropriately in accordance to that signal. So it will then send a signal through the efferent pathway to an effector, which will cause a change in the variable back towards set point. This is what our body wants to do. And whenever this works effectively, it is called negative feedback. when it works properly, bringing variable back to set point. Now, let me teach a little bit about what the set point I'm talking about is. So this set point is basically an area in which we want our variable to be at, the value we want our variable to be at. So that's exactly where we want it to be at. Now, because our bodies aren't going to maintain one value constantly, we are going to have a range in which we can remain healthy close to this set point. And our body will fluctuate throughout there, and everything within the range that is coming to and from set point is healthy. And that's just the value of the variable. So this is what we want to look for. This is generally considered negative feedback as well, because as you see right here, it is going away from the set point and then back towards, and then away from, back towards, and then constantly going to set point. And even if this were changed up a little bit to where our variable went outside the normal range, but as long as it went back to set point, then that would still be considered negative feedback. Positive feedback is whenever our variable leaves that range and doesn't come back. That means something within our system is broken. Maybe it is the efferent pathway to where it's not allowing the signal to get back to the effector. Maybe something is wrong with the effector that's not allowing it to release something. Or maybe it's the afferent pathway not getting to control center. There could be a list of different points in which the system can be broken, causing positive feedback. Inadequate feedback is going to be whenever the system can't quite overcome and compensate for the stimulus that is affecting the variable. And I'll give examples of each of these right here. Such as like negative feedback is where the system works properly. And that's, to give an example, let's say blood volume decreases. So our body is going to, which when our blood volume decreases, that's going to cause a decrease in blood pressure. Our body is going to want to respond. So it's going to increase heart rate, and it's going to increase peripheral resistance in order to get our blood pressure back up to a stable state. For positive feedback, something would happen to where if we lost blood volume, and our control center sent a signal which would decrease our blood pressure. But then our control center sent a signal for some reason to decrease our heart rate or decrease peripheral resistance, which would then cause the decrease in blood pressure. This would mean that our set point for our blood pressure is just not our set point. I apologize. But our variable's value is just going to keep getting further and further away from set point. So some system is broken and so it's going to get further from set point. This is gonna get back to set point. Next, we have inadequate negative feedback. And that's when something happens such as the loss of blood volume will decrease our blood pressure. Then our system is going to work properly by increasing heart rate and increasing peripheral resistance. But our blood pressure, excuse me. But our blood pressure is going to still remain low because the stimulus is too strong or the heart rate and peripheral resistance isn't strong enough, causing that blood pressure to not rise back up. Meaning it's inadequate. It's not sufficient enough. Now, to give an example of this, let's say we have a person. In my drawing, it's going to be not the greatest. I did not become a biologist for my art. So let's say that a cold front comes in, a cold wind. Our thermoreceptors are going to come pick that up. Then those receptors are going to send a signal through action potentials via axons on sensory neurons, which will then stimulate the hypothalamus, the control center, which then will send a signal through action potentials that travel via motor neurons, which then reach the muscles, telling us to shiver, which will help warm up our body. Now, using this example, I'm going to teach a little bit about hierarchy. Is another thing this cold wind will do is it will send a signal through the thermoreceptor and cause an action potential to be sent via axon on sensory neurons, triggering the hypothalamus to send a response. and then it'll send another action potential via the neurons to the smooth muscles of vessels to vasoconstrict. So it'll also cause vasoconstriction just through a different efferent pathway. And but this vasoconstriction will start with the extremities. And this is going to teach you a little bit about hierarchy. So it's going to start with the toes and then the limbs and then slowly move inward. Because the body is wanting to protect the most important organs, which is the heart. And so along with the brain and spinal cord and different areas of the body that it needs to be able to function to keep alive. If you lose a finger, it's not as important as losing a heart. You'll still be able to live if you lose a finger, but you won't be able to live if you lose your heart. So in this area, the blood vessels within the area are either going to stay the same size or they're going to vasodilate so that way they can stay warmer around the areas that they need to keep warmer. While these things can get colder, and that's okay. So we touched on set point variables. We touched on normal range, receptor, stimulus, control center, effector, efferent pathway, negative, positive feedback, and inadequate feedback. And we also touched on hierarchy. And I'm also going to touch on the definition of homeostasis, which I should have touched on a little bit at the beginning, which is just the maintaining a stable environment despite environmental changes. Next thing we're going to do is we're going to talk about feed forward. This feed forward is whenever your system adapts to a stimulus. Well, it's not even the stimulus at the point, it adapts to a response and causes an anticipatory response before the stimulus hits the system. So it's sort of like a pre-warning or premeditated attack on something that may happen. For redundancy, that is going to be when there is multiple pathways, multiple effectors, not pathways, that achieve the same goal So if one system fails, it still survives. Acclimatization is when your set point changes to adapt to consistent surroundings. So there's your overall video of homeostatic control center. Next, we're going to move on to different transporters. Let me make this one blue. So we're going to talk about 3 different types of protein-mediated transports. And I'm going to go through a different list of words. I'm going to write this down real quick that I'm going to touch on throughout it. So we have passive transport, active transport, concentration gradient, diffusion equilibrium, simple diffusion, selectivity, filter, voltage gated channels, ligand gated channels, mechanically gated channels, leak channels, carrier proteins. We're going to talk about saturation, GLUT2 transporters, which are in the liver, GLUT4 transporters, which are in the skeletal and fat, sodium, potassium, ATPase, also known as sodium potassium pumps, symport, and antiport. So to start us off, I'm going to talk about a little bit about passive transport. Well, before that, passive diffusion. Passive diffusion is when it uses a concentration gradient to move from something from high to low area of concentration. Concentration gradient is the amount of solutes from one area compared to another. Well, it's just the concentration of solutes in one area. The gradient is when it's compared to another area. it moves from high to low. Next, I'm going to talk a little bit about simple diffusion. The most common molecules for simple diffusion are carbon dioxide and oxygen. And with this, the graph that you usually see with simple diffusion is an ever-growing graph. Let me straighten that graph out a little bit. To where it's just constantly rising by rate versus concentration. So the more concentration, the more concentrated something is, the faster it's going to diffuse across. Then next, we have facilitated diffusion. And these use proteins. With facilitated diffusion, you can be saturated. This saturation will cause you to not be able to pump as many solutes through. So this graph is going to be rate by concentration. Whenever your concentration increases, it'll reach a point to where those proteins cannot push them through any faster than than the higher concentration you have. And this is going to be very true for carrier proteins, which will be saturated a lot faster than channels. Next, we have mechanically gated proteins, which we're going to get here. They are a type of facilitated diffusion. And mechanically gated proteins is when something in the environment is pushing open or close the gate. Voltage gated proteins is when if there is a charge component that causes the gate to open. Then we have ligand gated, also known as chemically gated. And these are proteins in which they are opened by a ligand. A ligand is a specific molecule in which the receptor on the gate will pick up that specific molecule. And then we also have pores, which these are also known as leak channels. These are always open, but they are specific to certain things as well, such as like you have potassium pores, you have aquaporins and others. aqua, which potassium pores are specific to potassium, and aquaporins are specific to H2O. So, and all of these here deal with charge and size selectivity. I mean, they are selective to molecules of a certain size or molecules of a certain charge to allow them through. It won't just allow anything through. It'll only allow those certain things. We're going to talk a little bit about Fick's law here as well. Fick's first law of diffusion. So that is going to be your net rate of diffusion is going to equal your diffusion coefficient, a negative diffusion coefficient, multiplied the surface area of the cell, multiplied by the difference in the concentration, divided by the thickness of the cell. So whenever you're, and so know that that will move in accordance to there. Next up, we're going to talk about active transport, because all of this here with the passive diffusion, simple diffusion, none of this requires energy. Now we're going to talk about the transports that need energy. And that is going to be called active transport. So the type of energy that it's going to use is ATP or GTP for energy. It needs at least one molecule it will help at least one molecule to move against its gradient. This is meaning it's going to go from a low gradient to a high gradient. The first one we're going to talk about is primary active transport. This directly uses ATP. One of the pumps that are very specific to this that we use in class a lot is a sodium-potassium pump, which has the specificity to sodium and potassium. It's going to let 3 sodium out, 2 potassium in. Then we have secondary active transport, which indirectly uses ATP. And that is going to allow for antiport which we'll hit these terms in a second, or symport. Antiport is whenever you have your concentration gradient one of them is going to go against the gradient. Because the system that used ATP created a concentration gradient that the primary active created a concentration gradient to where one gradient is going to go with and allowing the other one to go against. With symport, you're going to have a similar thing, except one is going to go against the gradient oh, that was wrong. 1 second. I just made too many dots. One is going to go with gradient, sorry. And the other is going to go against its gradient. Again. But they're both moving in the same direction. And next we're going to talk a little bit about a channel versus a carrier. So a channel is going to be open, allowing the solutes to pass through. And the rate is going to be much higher. And the saturation, which meaning, like I said earlier, the rate at which something can move through before becoming too concentrated, so that way it can't move through, decreasing the rate, the saturation is going to be higher than a carrier. The carrier is going to have only certain amounts that it can pass through at a time. And so whenever it opens and closes, it's going to, if this becomes super concentrated out here, it's still only going to be able to move as fast as this carrier can. And so the rate is going to be slower, and the saturation that means they can get saturated. Yeah, saturation level higher than carrier. This means it needs to be saturated less in order to still decrease the rate. And then as I talked a little bit about earlier, specificity is the ability to select certain substrates to pass due to size, charge, chemical structure, and there's a continual list of others as well. Next, we're going to talk a little bit about competition. That is when multiple molecules compete for the same transporter. An example of this is the GLUT transporters. Which these are carrier proteins. These are family glucose transporters. If the glucose is high next to these GLUT transporters, when let's say the GLUT transporter uses glucose and galactose. When the glucose is high, it's going to block up the carrier, not allowing galactose to access. And the same is in reverse to be said. So the glucose will keep being around the carrier while galactose won't be able to access. Or if the galactose was there, the glucose wouldn't be able to access it, etc. So only the glucose would go through. And that concludes our discussion on our transports and our mediated transports. Lastly, we're going to talk about osmosis. Which is the water movement across a semi-permeable membrane from low to high solute concentration. And just to show you a little drawing of this, let's say you have there's those solutes there and one solute there. Your water is going to move over to the one with higher solutes. Well, the green little dots are your solutes. Again, I'm going to touch on the list of words we're going to cover. We're going to cover intracellular fluids, which I'm just going to abbreviate to ICF. We're going to cover extracellular fluids. We're going to cover interstitial fluids. We're going to cover plasma, aquaporins, osmotic pressure gradients, solutes, and chemical disequilibrium. We're also going to discuss about osmolarity, we're going to talk about molarity, and tonicity. And then we're going to have some vocab within each of those. So first I'm going to start out with osmolarity. So that is going to be your total concentration of solutes in a solution over your solution volume. Usually this is done in liters, but it can be what somebody chooses. With osmolarity, it takes dissociation into account. Such as like if you have 1 molar of sodium chloride, when placed in water, it's going to turn into 2 osmoles because the sodium and the chloride will break apart. And so therefore, you'll have 2 osmoles per liter. Now, the reason why that's different than molarity is it doesn't take it doesn't account for dissociation. This is the concentration of a specific solute. Specific solute. So with that being said, if you have 1 NaCl, that's going to equal 1 molar NaCl. And then osmolarity is going to measure, like we said, total solute concentration over the volume versus the whatever you're comparing it to. Of both. So I'm going to teach you a little bit about what the intracellular and extracellular fluid means. So intracellular fluid means it's the fluid inside, right? The fluid inside. Extracellular fluid is a fluid on the outside. Interstitial fluid is a fluid that is in direct contact with the membrane of the out of the cell. So let's give some examples and teach some vocab here a little bit about isoosmolar, hypoosmolar, and hyperosmolar. Isoosmolar is whenever the inside of the ICF and the ECF are equal to each other. The hypoosmolar is whenever you're comparing the solution. You got to be specific on what you're comparing it to. On here, we're going to do the solution, so ECF, to the cell, ICF. And with hypoosmolar, the ECF will be lower than the ICF. Just like that, 150 osmolar compared to 300 osmolar. And with hyperosmolar, you're going to have a more osmolarity outside than you are inside. Now let's teach you a little bit about tonicity. Tonicity is the effect a solution has on a cell. With this, I'm going to show you another drawing as well, except this time I'm going to give you 3 different solutions in 3 different cells. I'll explain why I'm drawing each one here in a second. So if you have an isotonic solution, that means the cell is going to stay the same. And that is generally whenever and so that doesn't take into account for values, but the water isn't going to flow inside or outside the cell. It's going to be equal. So usually this happens with a osmolarity that is equal to each other for both the ICF and ECF. Then we're going to have a hypotonic solution. This is usually an occurrence whenever you have a solution that has more solutes inside the cell, so the water is going to want to rush in, causing the cell to swell. Then we have a hypertonic solution, which that one is when you're going to have a higher osmolarity and osmosis occurring outside the cell. So the water is going to rush outside, causing the cell to shrivel or shrink. Oh, let's not do that. Now with this, let me teach you a little bit about saline, dextrose, and then in the cell. I started giving you some examples of 300 and 400 for the hypotonic, hypertonic, and isotonic. But let me teach you real quick that inside the cell, your normal osmolarity is 300 milliosmoles. 5% dextrose and 0.9 saline is also going to be 300 milliosmoles. With this, but we also need you to understand that dextrose gets used up by the cell, metabolized by the cell. And it's permeable to the membrane. This will also explain how you can have a isoosmotic solution but have an but be a hypotonic cell. But it be hypotonic. Because if you have 300 milliosmoles in here, and you have 5% dextrose, which is 300 milliosmoles, that 5% is going to go inside the cell and get eaten up. Therefore, canceling it out, turning it to 0. So water, essentially turning it to 0. So water will want to flow out of the cell because there's less solutes there, causing let me change what I said there. There'll be less there, so it'll want to flow towards the solutes, causing the cell to swell up. And that is how you can have an isosmotic solution that is also hypotonic. And then aquaporins is what water travels through, and plasma is the major component, where water component is of the water component of the blood is. And then osmotic pressure gradients is the pressure gradients created by molecules and ions, which are known as solutes. The chemical disequilibrium is the non-equal distribution of the ICF and ECF that we see. And this is going to be our conclusion for answering all of our questions here. Thank you for your time.